Okay, we are recording now. Hey everyone, welcome to another YouTube video. And in this video, I'll be discussing about the distributed system and what is distributed systems, why you need to know about distributed systems, the various types of architectures involved in designing distributed systems, what is CAP theorem, and what is the significance associated with distributed systems, what is distributed processing, what is distributed storage, what is distributed messaging. All this will be covered in this entire video itself. So this video would be enough for you to get a good grasp of what is distributed systems and its architecture and its associated theorems and properties associated with it. Without any further ado, we'll go into the video. So what is a distributed system? So put in simple terms, distributed systems means a group of computers working together over the network, which appear as a single computer to the user. So let's take for an example a weather reporting or weather analyzing tool, which consists of millions of data points. So in order to analyze this huge amount of data, a single system would not be physically feasible to crunch those numbers, right? So in such a case, we will have nodes. That is a group of computers connected together over the computer network. And each of this processing node or computer will be assigned a task. That is, this huge set of data will be split among all these computers or nodes over the network. And this data will be processed, and the final result will be aggregated and then given to the end user, like in a single computer when you're doing or processing a file. So that is just a brief or like an overview about what is a distributed system. The next question would be like, why do you need a distributed system in the first place? Why can't we just like have one very powerful single machine that runs these kind of computations and activities, right? So why do we need a set of small computers clubbed together to perform this? The thing is that we have two types of scaling, that is vertical scaling and horizontal scaling. In the initial days, people went with vertical scaling. That is, whenever their application hit a bottleneck, that is, in terms of memory processing or in terms of network requests, people would just scale up their hardware. Like if their 100 GB memory is at a point they have hit the roof, then they will start buying more hardware to fill this gap. The thing is, after a certain point of time, you won't be able to scale your hardware. Your hardware will be limited by the time uh, by that time what is available. Like a particular time, the maximum amount of uh, storage uh, available would be like 1 TB or 10 TB in a single system, right? After a particular point of time, you won't be able to go beyond that scale, right? So that is why horizontal scaling is very important, and wide distributed systems are are being very popular in terms of storage and processing nowadays. If you look at this graph, you can see whenever you require extra capacity in terms of memory or processing unit, initially vertical scaling would be cheaper for you. And as you progress, horizontal scaling becomes much more efficient and much more scalable when compared with its vertical counterpart. So in distributed scaling or horizontal scaling, there are two main advantages when compared with vertical scaling. One is fault tolerance and the other one is latency. So what fault tolerance means is that like in vertical scaling, as you like buy a bigger system with additional hardware capabilities, if that system goes down, then your entire application goes down. It becomes a single point of failure. In horizontal scaling, as you buy your nodes, connect to your own network, even if one of your nodes goes down, the other nodes will serve your end users. So this makes your system more fault tolerant, and your data would be available across the nodes, and your data retention and durability is also increased. And one other major advantage with horizontal distributed systems is latency. Even if you buy a very powerful computer or a machine, and you're just vertically scaling your system, the network bandwidth will hit a cap very easily. But that is not the case with distributed systems. You can even set up region specific nodes. For example, you can have a node in US, you can have a node in Europe, you can have a node in India, and you could serve your end users or clients based on their location for better and more efficient, better latency and more efficient processing. So we can't have a distributed systems lecture without talking about the CAP theorem. So what does this CAP theorem means? So CAP, the full abbreviation means is that consistency, availability, and partition tolerance. What this CAP theorem states is that only two of the available properties can be applied to your distributed system at a particular given time. So your system can either be consistent and available, or available with partition tolerance, or you can choose consistency and partition tolerance by not having your system always available. So this is like your uh, as a software developer or an architect, you have to consider which property among these three, which two are mainly important for your system, and you should choose them for your distributed system design. So you can see that in my screen, consistency. So if I write a particular data in my distributed database, and if I immediately read that, and if the data is updated, then I could say that my system is consistent. But if I write data and if I try to immediately read the data, and if I'm not able to retrieve it, or an old data is available, then my system is eventually consistent. That means my system is prioritizing being available, and it is prioritizing the partition tolerance. It is an AP system, I can say, not a consistent system, but it will be an eventually consistent system. And for availability, for example, if I have three nodes in my cluster and one of my nodes goes down, then the other two nodes can serve my end users. This is the availability of my system. But in case if a write happens in one of my nodes and it goes down immediately without replicating the data to the other two nodes, then this data would be lost. But even though this data is lost, then I would still be having two nodes that will serve my end clients. So this is a kind of a trade-off, that my system will be available 24/7, but in case of some network issues or in case a node goes down, a certain amount of data could get lost over uh, because it is being available all the time. So either my system can be available all the time, or it can choose to be consistent all the time. And this trade-off is to be decided based on what software architecture the engineer is supposed to go with. Now, you might have heard about ACID properties in databases, right? Similarly, like that in distributed databases, we have something called as base properties. So what does this base means is that basically available software and eventually consistent systems. So basically available means the system is always available, because in distributed systems, we have multiple nodes. Even if you lose a couple of nodes, your system is available, but it may not have the data that is up to date, but your system is always available. Soft state means that the system state can change over time. So if I do a write request for in one node, then this node will then replicate the data to the remaining nodes in my cluster. So if I do a write request in one node, if some other user then requests the same data to be read from a different cluster, then immediately that data won't be available, but the system state will be changed over time. And for eventually consistency, for eventually consistent system, this base property does not obligate immediate consistency, but over a course of time, all the nodes will have the latest up-to-date data. That is what eventual consistency means. So coming to the next topic is consensus in distributed systems. So what does this consensus mean? So consensus is nothing but a set of computers that is agreeing on a single value or a single point that one of the nodes in the systems proposed in in which is opposed to making up a random value. So this the challenge in agreeing this group of computers agreeing to a single value is that a particular node can fail, machine can fail when you're doing it. So there are several algorithms like the Paxos algorithm, and there is a Raft algorithm, consensus algorithm that deals with this problem and makes distributed computing and processing possible. So uh, I'm not jumping on to these algorithms and theory in detail in this lecture, but if you're interested in, you could Google it up and you could read those research papers for your own information. Next step is distributed computing. Uh, in the starting of the video, I would have explained that for like processing, like for example, a huge weather report which contains millions of data points, we will be splitting up those data across multiple computers or multiple nodes and aggregating the results again. So this is basically what distributed computing means. And in the market, we have several distributed frameworks such as MapReduce, Spark, etc. MapReduce was introduced by Google in 2004 in a research paper, and it is a very popular framework until Apache Spark came. The thing with MapReduce is that it takes too much memory and too much time. And in case if the processing fails at a particular point, then the processing will have to be redone. The mappers and reducers has to be recreated. But in case of Spark's lazy evaluation and lineage, even if nodes are like going down, then we can still trace back and process data, which is like 10 to 15 times faster when compared to MapReduce. So MapReduce was a Spark that I'll cover in another video. In this video, I'm just focusing on distributed systems only. So in distributed system architecture, there are two widespread architectures that will be discussed. One is the Lambda and Kappa architecture. So in Lambda architecture, initially we will data engineers will be doing batch ETL pipelines. That is, they will extract data from a particular or a various types of resources, then put it into a common space, then do transformations over that using SQL or other processing frameworks, then load it into the required databases or generate reports based on it. So Lambda architecture comprises of this batch ETL processing plus real-time processing architectures such as Spark streaming, Kafka streaming, etc. Kappa architecture only deals with real-time processing architecture. In this type of system, every single thing will be pointing to uh, uh, real-time data bytes. So every point would be a producer, and uh, uh, every endpoint would be a consumer, where you'll read from a centralized data unit or a data warehouse. So that is enough about distributed processing and distributed computing. And there's a distributed file system, and uh, the most predominant one is HDFS, that is Hadoop distributed file system. So in Hadoop distributed file system, we will have a name node and data node. So name node in this architecture stores all your metadata, file location, everything. Data node consists of file blocks. So you can think of like in your system, a single file will be stored in a single location. In HDFS, this single file will be split into multiple files and be stored across different data nodes. And this name node will contain the metadata information on where it is stored and where the data is replicated. One of the main advantages in storing data like in this fashion is that even if your nodes or computers go down, then the data can be replicated and retrieved, making it much more fault tolerant and efficient. There's also, however, a disadvantage that not many people will speak about it. That is that if you store small files or files that are in less volume, then this is not an efficient approach, as your name node metadata will be much higher compared to your compared to the actual data that you're storing. So HDFS is suitable for only for storing huge big data files. And for finally, for distributed messaging systems, you have something like Apache Kafka, where you'll be having a producer, broker, and a consumer architecture. So you various data points can be produced from various places into a single broker. And this broker will consist of multiple topics or message queues if you are from a Java background. Uh, so this topic can be read by multiple consumers at the same time, thus making it loosely coupled system. So that in that case, your data can be read by multiple teams and multiple systems without creating much overhead on the messaging system itself. So this is a quick overview of what you need to know about distributed systems in this video. So in other YouTube videos, I will deep dive into Apache Kafka, Spark, Hadoop, etc., and internal components, and how to do hands-on exercises and everything. So if you guys enjoyed this video, then like, share, and subscribe. And yeah, thank you guys for your time.